Good. So yeah, it's nice to be here in person. I was here virtually about a month ago. And this time I'm going to tell you about a different experiment in my lab. We have created an optical lattice that has sound, so allows atoms to move around. So this is done by a trio of wonderful graduate students, one of which has already obtained his PhD, Yudan Guo, Roton Croze, and Brendan Marsh. And very fortunate to have two really fantastic theory collaborators, Jonathan Keeling at St. Andrews and Sarang Gopal Christian, who needs no introduction. He's here at this conference. And so please talk to him if you want to know the real story. So the star of the show is a cavity QED experiment. It's a little bit strange. Instead of a single mode cavity QED experiment, it's a multi-mode system where many modes of the cavity are degenerate and resonate at the same time, actually thousands of them. And that allows one to create a flexible lattice of light in the middle. That's this green-blue color field, where atoms in this yellow-orange colored space here can form a checkerboard that can wiggle back and forth and have vibrations or phonons. The system's pumped by multiple colors of light. We can drive it and do dynamic susceptibility measurements of the system. So I'll be explaining what this system, how it works, and what it's capable of. All right, I'm sure this is working, so I'll do that. Okay, so just to set up why we're interested in doing this, let me just note the obvious, which is that traditional optical lattices are silent. If you put your ear to them, you don't hear anything. Okay, you can't do that in reality. And that's because they're a simulacrum of what you actually have in reality. So in reality, as you cool a liquid down, the electrons, the ions of the system conspire to break a continuous translational symmetry, a U1 symmetry, in space, where they have some fixed periodicity, but where they actually sit into that row is determined just kind of by random upon each freezing. Whereas in the optical lattice, the periodicity and the spacing, all of that is hardwired in by just how the experiment is constructed by hand. So, a graduate student takes a laser, puts a mirror, and retroreflects the laser, and that's where the lattice is, wherever that mirror happens to be positioned. So there's no dynamics there. So you don't get any of the elasticity that you expect from a real solid. There are no phonons like you see in this cartoon. So, what you miss in all of this are the Goldstone mode dispersion relation that you enjoy and know about from basic solid state texts that describes the energy versus momentum dispersion or relation of acoustic phonons. Okay, this linear relationship that tails out. So what you like to do is to somehow build back into your optical lattice system the crucial ingredients that can give you these excitations in something that you're dealing with atoms and photons. So you need to have a continuous translational symmetry, and you need to be able to break it. And second, you need to have local interactions. So you need to be able to exchange momentum locally in real space so that you can get some of this distortion arising from that exchange of momentum, okay? So you need both of these ingredients. One of these has already been created. So in the system of two-mode cavities or dipolar VECs, folks have made kind of a periodically modulated superfluid with only the k = 0 excitation. Okay, so that's just this point right here. So it's kind of like the whole thing rigidly moving. All right, but no flexibility of that excitation. All right, so that's been done in these groups here. So that's a kind of a supersolid without sound, or lattice supersolid, or you can debate whether you should call it a supersolid. That's what this is known as. What we have done by contrast is to make a supersolid with vibrations. All what we mean by this is just that you have a superfluid that has a translational symmetry breaking, and it has acoustic phonons in it. Okay, not just at k = 0, but along this whole dispersion. So let me now describe how we've made this. And this is going to go into the weeds a little bit, but I think it's interesting. It's how we create such a system, because we can change different aspects of it to engineer a host of other types of dynamical lattice systems that you might want to discuss and tell me about and figure out what might be fun to do with it. Okay, so the way we engineer this is to take a single mode cavity, which you might know and love, where you have, say, atoms in the middle between two mirrors. They resonate only on a single mode, and you can pump photons into the system by driving a laser transverse to the cavity axis and have those photons exchange from like coherent scattering from the atoms into the cavity, like so. So what is the mode spectrum of such a cavity? This is just the textbook Fabry-Perot cavity spectrum, a single mode cavity. It's a little bit more detailed than your standard book might provide you, but it's important, so let me go through it a bit. So as a function of frequency of the cavity, you have different resonances. These are the TEM modes, the Hermite-Gaussian polynomial kind of shape that you might know about. They're separated into mode families, indexed by this letter Q, and that just counts how many nodes there are between the two mirrors, okay? So say at the Q-1 family, you have the zero order resonance. That's the Gaussian mode, okay? And then generally, let's say at higher frequencies in this particular cavity, you have ducklings, little modes that extend to higher frequencies. This would be like maybe the TM01 or the 02 or the 32 or whatever going forward, okay? What's not generally recognized, or at least mentioned explicitly, is that each family alternates in the phase of the longitudinal mode, okay? So let's call this family the sine family. The one just to the right of it, higher frequency, would be the cosine family, okay? They all have the same kind of transverse indices, the L plus M indices. These are the number of nodes transverse to the plane. But they start at kind of a different phase shift from the mirror, okay, by the time that they hit the center of the cavity, all right? And then if you go back, you get the negative cosine, and then you go here, you get the negative sine, and then it repeats, okay? It has that symmetry. So that's what a single mode cavity does. What we, to enable this dynamic lattice, this pliable lattice, what we use is not just a generic cavity where you just take any old mirrors and kind of put them opposite to each other. We create what's called a confocal cavity, which has a very, very specific geometry. In this geometry, the radius of curvature of those mirrors exactly equals the length of the cavity. Okay, R is equal to L. And by exactly, I mean this is down to, a sub-micron level, all right? And so it's very hard to engineer experimentally, but you can do this. And when you do this, what happens is as you get close to this condition, you start to rearrange the order of these higher order modes such that a new family emerges, which maybe has the same Q, the same cosine-like fundamental Gaussian mode of the family in the single mode cavity, but its ducklings have been rearranged. They swapped kids, okay? So you have, so this one will take the second order red mode, or the sine-like mode, from the family just to the left of it. And then the next mode after that will be, say, the fourth order one from two families. And then so on and so forth, like so, as you get close to this degenerate condition, right? And these, I've drawn them kind of separated out just so you can see them, but if you've done a good job experimentally, these are all at the same frequency exactly. There's going to be some imperfections, okay? We're not perfect. There's going to be some bandwidth of, some dispersion. But in principle, these all line up at exactly the same frequency. And you might notice that I've only drawn even order modes, and that's because the confocal cavity distinguishes between odd parity and even parity. And so in between here, you'd have all odd modes before going to the all evens again and so forth. But we can just focus on this family because we're going to send in a pump field that is red detuned from this fundamental closely enough so that it looks like all of these are degenerate from this spacing, but this spacing is not so large as to start involving other families. Okay, so this is an example of an experimental transmission. Okay, we've actually done better than this more recently, but you can see that this is not just one Lorentzian spike. There actually has some structure here. If you analyze this, you can convince yourself that there are thousands of modes within this 20 megahertz bandwidth. We've now reduced this to about 5 or 6 megahertz bandwidth. So we can do a pretty good job of making a degenerate cavity. Okay, so what does this mean in terms of this picture of momentum exchange that you need as the ingredient to make a dynamical lattice? Well, what we mean is that you can actually mediate interactions via the photons that are in the superposition of all these modes that then scatter between the atoms. So an atom that receives a photon from the pump field can virtually exchange that photon with another atom at some position away and then receive it back before scattering it in the forward direction. So you get this interaction via scattering these virtual cavity photons. In a single mode cavity, you just have an all-to-all kind of interaction because that photon is everywhere in that Gaussian mode. But in the multi-mode cavity, that photon is in a wave packet that is local in space because it's a superposition of all of these Hermite-Gaussian polynomials that are supported by that cavity, that degenerate cavity, at the position where that atom happens to reside. So it'll see all the electric fields from all of those photon modes, take a superposition of that, and of course the superposition are these TEM modes, and if you sum over enough of these, you get a very localized wave packet. Okay? So the photon in a multi-mode cavity is a localized wave packet, and that's the new ingredient that we've introduced into cavity QED. Okay? It's not everywhere, it's localized in space. And this is known in the literature as a super mode. Okay? Everything has to be super, of course. We've created ones that are about 2 to 3 microns wide. So if the fundamental mode is about 40 microns in diameter, we can make something that's more than order of magnitude smaller. In fact, we've gone down to like 1.5 or 2 microns. Okay, so you can really have a huge electric field spike due to this superposition. This is what a cartoon of what it really looks like. You actually have 2 super modes. You have one where the atoms are, and then a virtual one nearby because of the even or odd symmetry of the cavity. Okay, so you actually get a doubling of everything, but never mind. What this means for the cavity parameters is kind of interesting. So if you take a single mode cavity that naturally gives you a coherent coupling strength G that's about 1 megahertz, and you've coded it well enough so that the losses or the photon or the electric field emission rate is about 1/10 of that, you can get what's called the cooperativity, or the ratio between the coherent and the dissipative dynamics or rates. That's greater than 1, so it's in the strong coupling limit. But that's not really the cooperativity of the system. It's actually far higher, because really what an atom sees is not just one of these modes, it actually sees this electric field spike because of the geometry of the system. And so really the cooperativity for the system can be 10 to 20 times higher. Okay, and we've measured that fairly rigorously now. So we have systems that are kind of, nearly record-breaking, maybe record-breaking cooperativities. And that directly relates to the quality or the fidelity of the quantum states that we can generate in the system when you get up to C's that are 50 to 100. All right, so I haven't told you exactly how we engineer this translational symmetry that can be broken, as well as this local interaction. So let me delve into those nitty-gritty details. What we're going to do is to double pump the confocal cavity. So we're not just going to use one pump field of a particular color of light or wavelength of light. We're going to use 2. And the reason goes back to this alternating change in the phase of the longitudinal field. If you just pumped on this family here, there's no continuous symmetry to break. You're just locked into this cosine. But if you were to pump both on this family and this family right here, then you make coherent superpositions of every single, pairwise, every single mode, transverse mode, but with a longitudinal field that is either sine or cosine. So you add sine and cosine together, coherently, and now you have translational symmetry. Okay? So that's what we will do. We'll copy everything and do it twice. So it takes a lot of engineering experimentally, but you can do this. So let me run through just sketch the mathematics of what this looks like. So if we take the total potential, that which arises from this exchange of photons, we can divide it up into the potential which arises from this blue pump and the potential that arises from this red detuned, or let's call it the red pump. All right, so the blue pump can be broken down into two pieces. There's a piece that is proportional to interaction strength U0, which is all the cosine terms. And if you look at the exchange of photons, you get a term that looks like cosine K recoil, that's the recoil of the light, times Z, times the same thing with Z prime. Those are the two different positions of the atoms at Z and Z prime, okay? And you get the same for U2, but U2 is now the even ones, okay? And it's proportional to the sign because it's the red ones here, okay? And if you work out what what U naught is from taking the mode function, which is this Kavli with this index 0 mod 4, which is all those L plus M's mod 4. And if you work out what this sum looks like, it looks like this thing, okay? It's kind of weird. It has two terms. It has a local term, which is, it's a Bessel function, which has some interaction range, Kavli here. This is a local interaction, which gives you the ability to locally exchange momentum. Plus it has a long range term, a non-local term, that's Euclidean, but it's not translationally invariant. This you want to cancel out for this particular project, because this would ruin our ability to have a dynamical optical lattice. But for a lot of our work in other areas of my lab, we're exploiting this term to create spin glasses and spin-dependent Hamiltonians. If instead of looking at the motion of the atoms, you do all this with spin states, this is a very fascinating term for exploiting to make spin glass physics. But that's a different talk. What we'll do now is look at this term here. And the key point of this term here is that you get the same local interaction, but the non-local term has the opposite sign, okay? It just comes about because of these different mode functions. So when you do this double pumping, you get this second terms from this red detuned pump, which is the U naught term, but with a different longitudinal type interaction, which is sine rather than cosine. You get everything kind of mixed up, but when you add everything together, rest assured that because of this minus sign here, this term cancels, and the total interaction you get is simply this local term here, okay? So this, in one fell swoop, gives you both a system that has a U1 symmetry, it's translationally invariant, and it has this local interaction right here. It has a finite range of interaction, which again, we've created in real space. If you look at real space, is just a few microns compared to a system that's tens or 100 of microns in size. So experimentally, we can verify that we're doing this, and this is one piece of evidence. I won't have time to tell you the others. But if you just pump with one field, and you look at the phase of the lattice that you make of atoms, which we can actually measure, you look at that phase, then it generally scatters about just one part of this 0 to 2 pi kind of, color wheel. But if you add the second pump, which are these circles, you see that randomly you scatter across the entire 0 to 2 pi, okay? And that's this emergence of this translational symmetry. Okay, so this is what the apparatus actually looks like, and this is only part of the room. And yes, my students do know what every wire and cable and fiber does. I might not anymore, but I think I could probably figure it out. And in the center, buried here, is a vacuum chamber with these two mirrors that are opposite to one another. These are very carefully placed so that they exactly realize this confocal configuration. Okay, and that's not an easy thing to do. Normally when you do cavity QED, you kind of put them wherever, and it's fine, it doesn't really matter. But here, it actually matters down to the submicron level. And then between the two, despite having all this stuff in a vacuum chamber, you can still have a low enough pressure to create a BEC of rubidium. And we do this every 10 to 15 seconds with, hundreds of thousands of atoms. How do we detect what's going on? Well, we have a new way of detecting what's going on in a cavity QED system. So, it's been well known since the 90s that cavity QED is wonderful for real-time detection of quantum systems. You can look at a quantum trajectory of the system by just reading out the light that comes out, either with photon counting or heterodyne. But we can do something a little bit more. Now what comes out of the system has spatial dependence, not just temporal dependence. And so we can beat some of the light that goes in to pump the system, which forms a local oscillator, against the light that comes out, interfere it together to get these stripy patterns. And those stripy patterns can be analyzed just like you analyze a hologram. Okay? This is called spatial heterodyne, or it's making a hologram. So we can deconstruct those to get the amplitude and the phase of the light coming out, plot them together with a color wheel with an amplitude to give a hologram of the light coming out, which tells you that, yeah, there's light, there's a super mode here coming from atoms here, and this is its mirror image. Okay, so we're going to ignore these mirror images. They're just redundant information. But this is a really neat system that is novel, adds novel capabilities to the simulation of quantum systems with atoms and photons. And it kind of extends this notion from Marcus Greiner of a quantum gas microscope. Because now, instead of just reading out the light passively, that light gets reflected back onto the atoms to mediate the interactions. And so we refer to this system as an active quantum gas microscope. We get spatial information because of that light, but the light actually is what drives the interactions of the system at the same time. So it's a wonderful system to use. Okay, so how do we generate the lattice in the first place? We generate it self-consistently through a superradiant phase transition. So I flipped things on the head just to save room, but you have the atoms here, you pump it, and if you pump beyond a particular threshold, which you can calculate easily, you get what's called a superradiant transition into a checkerboard structure. This is akin to the well-known Dickey model, okay? And what that does in real space is to give you a checkerboard of the atoms. And if you look at the light, you get a burst of light coming out, a superradiant pulse. Together, these are the kind of dual manifestations of the density wave polariton that's created inside the system. This is the matter wave part of the polariton. This is the optical part of that polariton. And yeah, so that's what you get out. Now, it's really hard to image this structure that's wavelength, but you can look at it in momentum space by dropping it. And in momentum space, you can see that you get a checkerboard pattern by measuring the spacing of these Bragg peaks. So if you just sketch this out as kind of a map, you take the ground state of the system, which is the condensed state that you've put in there, in momentum bases of x and z, and this two-photon process in 2 dimensions gives you these Bragg peaks like so at these 4 corners, plus or minus these recoil momentum. Okay, so what we're doing is kind of a take on this like 10-year-old technique, 15-year-old technique, is to double pump the system. And when you double pump the system, when you look at one of those Bragg corners, now you can actually wiggle that Bragg peak around dynamically. Because because you can scatter light not just into the fundamental mode, but into higher order modes, you can take the momentum, the effective momentum of those higher order modes, and add or subtract that to the light that is used to create this two-photon transition. Okay? And that just mentally make the connection that these higher order modes, the L's and the M's of those higher order modes, are proportional to the transverse photon momentum in those higher order fields. So K perp is like L and M, and if L and M are like 10 or 20 or whatever, then you can actually have a substantial change in the momentum in this transverse plane, okay? And that happens in a self-consistent dynamical way, not by hand, okay? So you'll get a little bit of a wobble of that peak. And so if you sketch this diagram out, each of these peaks will kind of, they'll shear in a coordinated way, but you can actually shear them back and forth like this, like a trapezoid, okay? And so to make a movie of this is what the phonon looks like. This is that excitation of the phonon. It's a transverse phonon where its propagation direction is this way, its propagation is in X, but the oscillation is in Z, okay? Because that's where the translational symmetry is. Okay, so let me just show you 2 experiments in the time I have allotted. that kind of benchmark the system. So the first experiment we're going to do is to pump the system below threshold of the superradiant transition. And we're going to look at a Roton dispersion. This is just a density wave dispersion. Okay, Roton is just a fancy word for that density wave, softening. And we're going to see it in a k-dependent fashion. So here's that cartoon I showed you at the beginning, and now you can understand some of the pieces of it. This is the atoms. These are the two pump fields that are combined into this pink light that transversely pumps the system and is retroreflected. That populates the cavity as the green light here, back and forth. And now what we're going to do is use a digital mirror device to structure some
back on the dried fruit
into the cavity.
Yeah, dried fruit too. You know, so I have a big thing of raisins.
I just talk over.
Or? But
you're welcome to give my talk.
Because Mark's not really into raisins, but
Okay, cool. Yeah, it's like God is speaking to me. All right, so someone's very interested. All right, so you have the DMD, which it's a spatial light module. It's a device that allows. It's actually what's in this projector right now. It allows you to shape patterns of light. Okay, and you inject that into the cavity at the same time as you're doing that, and you can stimulate the system in a particular vibrational mode. And then this is where we take the hologram coming out here. All right, so what we inject are these patterns of light. We can do, like, say, 6 of them, where if you just focus on this upper little patch of light here, this one is all the same color, it's like blue. But this one starts to be one full rainbow, 2 full rainbows, 3, 4, 5. Okay, this is the different, these have increasingly higher K vectors of the light that's being injected. And what we should see is that you get more and more wiggles as you inject with more and more, with higher K vectors. And how we're going to measure this is to go a little bit below threshold where there are no Bragg peaks, inject this light in, and stimulate some atoms into higher momentum peaks with this light. Okay, so it's a dynamic susceptibility measurement, and you get some resonant peaks right where you have the softening Roton mode. If you do this for many different frequencies and many different momenta, you build up dispersion relations. So well below threshold, you get something that doesn't really have any dependence on the momentum. But then as you get close to the Roton softening, to the density wave transition, you see that it takes it becomes more stiff, this dispersion relation at higher momentum. So you see that this dispersion relation is kind of building up as you get close to the transition. All right, so this softening here has been seen in single mode cavities, but the rest of this has never been seen before because this is the first experiment with spatial dependence. Okay, so the last experiment I'll show you is the Phonon dispersion relation above threshold. So we're going to do the same measurements, but now pumping above threshold. Now this gets a little bit more complicated because above threshold, okay, just 2 more slides, so we're almost done. So above threshold, you already have peaks. So you can't just like say, are there peaks or are there no peaks? Because there are already peaks. And the little bit of atoms that you stimulate aren't really that detectable. So you have to be a little bit more clever. And unfortunately, I have a very clever student who figured this out, Yudan Guo, where if you, instead of just looking at the density, you actually look at correlations, then you can detect this little signature of a stimulated system. So let me explain how that is. So in real space, what we're trying to detect is a distortion of the lattice, which in momentum space is a blurring of those peaks, okay? Because you've distorted the lattice with the phonon, you're going to move these peaks sideways a little bit. So you want to compare the shape of this peak to what it would be otherwise. So to compare that shape, what you do is you look at momentum correlations, and you look at the differences in those shapes, momentum space, and then you plot that. And when you plot that, okay, the signal to noise is not quite as good, but you can definitely see that there is excitations. And when you plot that in this diagram like so, in a dispersion relation of omega versus k, you can clearly see what, within our experimental resolution, is an acoustic phonon dispersion relation. We have some linear part that's starting out, and then it starts to saturate like so. Okay, so So what is the speed of sound? Well, you can calculate what that speed of sound should be, giving some given the effective chemical potential and interaction energy, and it's about 20 centimeters per second. So if you were to be able to put your ear to this and listen to it, it would be about 1 kilohertz, which is definitely within your hearing range, unless you've played in a lot of rock bands. So this is something that is noticeable, right? It's a noticeable speed of sound of a lattice. All right, so let me just present you with the summary and outlook of where one could go with this. So with an optical lattice of sound, we've created super solid with vibrations. Okay, it actually jiggles and wiggles around. That's what this orange diagram looks like. The atoms are playing a dual role here. The atoms both create the lattice as polaritons, and they serve as the itinerant electrons because they can flow through the lattice at the same time. Okay, so that's fine. But the analogy would be a little bit kind of cleaner if we put another species of atom in there, different isotope, different spin state, whatever, to be the itinerant electrons in the kind of swimming in the sea of this dynamical lattice. And we can definitely do that. That's no problem. And then doing this can lead to several things. It can lead to kind of a more faithful emulation of exotic superconductivity. You can use the lattice light to give you some interesting pairing, okay, and then you have the phonons there. You can look at quantum elasticity, and this is something that Srang is very interested in. You can look at defects in the system. You can use this to look at quantum acousto-optical experiments, kind of the counterpart to the experiments that people do with membranes or superconducting systems. We can do this now with atoms. You can look at electron phonon physics related to polarons, and that complements what people have already been doing with atomic gases, but this in a kind of a different context. And then you can look at strange metal physics and linear T resistivity. Okay, so with that, I will now just again put up my group. This is my group prior to COVID. I need to take a new picture. But again, the folks who did all the hard work are here, and Srang's in the audience somewhere. We've also, I told you about that term, that cosine R1.R2 term. You can use that to create spin glass, and you can use that spin glass to do neuromorphic optimization computation, in particular, make associated memory, and we have a paper here that explains what those capabilities might be. And in other work, earlier this month at KITP virtually, I talked about this project, which discussed a new type of topological pump into strange states that can be called quantum many-body scar states in one-dimensional dysprosium. And we have a real experiment where you can actually put real superconductors inside of it, like pneumatic nictide superconductors, iron-based superconductors, and use BECs to image how the electrons move about through them. We did that and looked at the electron pneumatic transition a few years ago. Okay, thank you for your patience.
I guess we got quite a bit of time for questions. There's a question from the online audience. David, please go ahead.
Hi, Ben. Nice talk. Sorry I can't be there with you. So the question is, when you have this lattice forming, what's the depth of the lattice, and what's the occupancy roughly of the lattice? And does it make a difference if you're like far to one side of a superfluid magnet insulator transition, or what? I mean, you haven't really mentioned those kind of experimental elements.
Yeah. So you start with nothing, okay? There's just vacuum fluctuations. You ramp up the power, you go through threshold. Threshold happens at several E recoil.
Several being like 3 or 4?
Yeah, I don't know, it depends on the settings. It's not 15 and it's not 2 or 3, it's somewhere in the middle, depending. Right. And then we usually go to about a factor of 2 above threshold. That's where things are kind of nice and stable to take a lot of this data. But people have gone very far above threshold to see a superfluid mod insulator transition. Okay, You can do that. What that would look like in this system, I haven't thought about too much. But we so far are in the nice superfluid realm of this.
I see. And then the average occupancy in the superfluid region is what about?
The density, it's probably on the order of tens. Yeah, I don't know the exact number per site, to be honest with you.
Okay.
Yeah, but I can get you that very soon.
Okay, great.
In this experiment, we went from little tiny dots to surfboards of like 100 microns by 20 microns. And so, you can change that occupancy by orders of magnitude just by changing the shape of the trap of the atoms. So it also depends on which regime you'd want to know that in. Yeah.
Thanks.
Hey, nice talk. So I have a couple questions. The first is this U1 symmetry that you realized. How accurately is that realized? And can you break it controllably, or are you stuck with this?
Yeah, so I presented that data with the color wheel where there's like little dots. So when we are not creating that, you can see that we have, maybe an eighth of 2 pi kind of noise. But then when we do create the U1 symmetry, it's, fairly randomly distributed from 0 to 2 pi. And that's a direct measure of how well, in some measure, we've created that continuous translational symmetry. Had we not done that very well, we would not have seen the dispersion relation. And within our signal to noise, it seems pretty good. Of course, there are things that do break that by hand. It's a finite size system and so forth. But it's at least within our experimental resolution and the timescales we look at the system, it's not so bad.
And so the other question, if I can, is so I guess you're working with relatively high occupancy, maybe you said 10 or something, if I remember correctly. For some of the quantum simulations you talked about, probably you'd want to push towards 1 or 2, fermions as well.
Yeah,
is
exactly.
This feasible, or is this?
It's certainly feasible to do this with fermions. It's certainly feasible to go to lower occupancies by increasing the pump or diluting the gas. And people have done this. Esslinger's group, I think Hemmerich's group has seen the monoinsulator transition. So it's not a problem.
Very nice talk. So my question is, in general, when you want to prepare some steady state, some states of matter, you have to go to a steady state. And general dissipation, it's going to play a role. So what is the role of dissipation in the experiment, and how?
Right, so you can work out an effective theory for the system and pull out an effective temperature. And that's proportional to kappa, it's proportional to delta C, which is the detuning.
It's proportional.
It's proportional. So the effective temperature, that is. And so you can change that effective, changing kappa is hard because you have to recoat your mirrors, but, or do something else. But delta C you can tune, okay? So you can tune it to be hotter and you can tune it to be colder. And that's, you can look at it as a temperature, you can look at it as a time scale as well. And so depending on what you're interested in, you either have to work very fast before 1 over that, or you just work with a steady state system that's coupled to the bath outside the cavity from that back reaction. And you can look at the shape of that bath on the edge of the Lorentzian of the cavity and pull out the effective temperature and know where you are in this. And so depending on what you're looking at, that might be too hot or it might be just right. Okay.
So, but if you tune very far, that is where you are unitary, maybe the dynamics is too slow. That's the problem.
Say it again, sorry.
If you tune very far, the problem is that the dynamics becomes too slow.
Yeah, you have to pump harder and you get too much spontaneous emission. Yeah, that's the price you pay.
So thanks for the beautiful talk. So the photon mode is very localized, you said. So this lattice modulation in the picture that you have, it seems very broad, like it seems to happen everywhere. Is it really what it is, or is it just a cartoon?
Yeah,
or it happens only locally in those 2 microns? Because I assume that your condensate is probably 10 micron wide, right?
Right, that was my fault. I gave you a misleading picture. So it is true that any given exchange of photon is local, but there are many of those happening all at the same time. So kind of the field is everywhere, And the picture I gave you is just between two atoms, but there are tens of thousands, 100,000 atoms that are all exchanging photons at the same time, virtually. And so that is what gives you this field happening everywhere.
Oh.
Okay. Yeah, sorry, that was my mistake in presenting a misleading picture. Yeah, hey.
Sure, yeah, very beautiful results.
Thanks.
I was wondering, when we talk about supersolids, there's also the diverse supersolids around, and I was wondering if there's, how I should think of these two in relation with each other. Is there like very qualitative differences, or is it here, is the feature here that we have additional light field, or you can read it out, or is there something beyond that?
There's some obvious differences.
Yeah.
One, the dipolar supersolids are like 2 lattice sites, maybe 3. Okay, so you might ask yourself, how does that comport with kind of, a basic understanding of a solid? The modes that have been explored there are really just like kind of, stretching and center of mass modes, which are very different than a Goldstone mode. Leaks the Goldstone dispersion. So what they've measured there is the K equals 0, which is kind of like just the whole thing translating more or less, but not any higher order, higher K modes. It's not driven dissipative. They're all metastable in some sense, but it has a different character in terms of dissipation. Yeah.
Maybe I ask one question myself. So dissipation, as you said, actually plays a role in the systems, and also is going to change the nature of the phase transition in the system.
Yes.
Have you also looked at that? Slinger and Slinger's group have specifically looked into that, and I guess their conclusion was effectively thermal phase transition. Is it also going to be the case here?
Well, it's a fascinating question. I don't know if Sarang's in the audience, but his PhD actually was involved asking that question. It turns out that if you, in this particular system, it's going to be a non-equilibrium phase transition with exponents that I think are just like in the classical transition, just like the single mode cavities of Esslinger. But if you make the soft modes not just in a line, but make it in a ring, which we know how to do, then you get additional fluctuations. You increase the dimensionality of the system, and that gives you what's called a Brzozowski transition. And that is not a classical transition. It has different critical exponents. It's a weakly first order transition. And it comes about because you get this organization on a ring, and you get the additional dimension, higher dimension with the fluctuations, and that renormalizes the Landau parameters of the action. So we tried to actually do that already. We have to re-engineer the system a little bit to get into that sweet spot. I definitely think it's possible to do.
That's very interesting. Yeah. Just one last question, if there is no question from the audience. So if I remember correctly, the coupling in your system is exponentially decaying? Is it
the coupling?
The coupling between atoms. So if you write sort of an effective atom-atom interaction, is it...
it's the Bessel function. It's an exponential divided by square root of the distance.
Right.
Yeah.
So does it strictly have a phase transition? Is this 1D or is it a 2D system?
Well, regardless of the shape of that, it still has the superradiant transition. So
I guess if the dimension is, I guess in the single mode case is effectively infinite dimensional, right? It's a mean field model.
Yes, and in this, it's fine. It's going to be the dimension of the real space because it's no longer all-to-all connectivity. Mm-hmm. Yeah.
But I would think in low enough dimensions there wouldn't be a phase transition. I guess there can be a crossover, but depending on dimensionality.
Yes. Okay. It's it's a 3-dimensional system. Okay. It's not like close to 1D or 2D. I don't think it's in the danger zone of that. And it would be pretty finite size regardless. So, yeah.
Thanks. Okay, this is perfect timing. Let's thank all the speakers.
All right. Thank you.